Okay. So physical properties of the hydrocarbons. As I've been saying, as we've been kind of going on through this course in various capacities, if something's made up of just C's and H's, then it's a non-polar substance. We now know that from our last chapter, where we looked at the shapes of those types of molecules, and whether carbon is sp3 hybridized or sp2 hybridized or sp hybridized. If they're full of hydrogens, then all of those dipoles are pointing in opposite directions, and those dipoles cancel out. Even if the chain is long, even if we've got a long chain of hydrocarbons, on the overall, large scale, the carbon-carbon bonds have a delta En of 0. The carbon-hydrogen bonds, I can't remember what the delta En was. I think it's around 0.8 or something. It doesn't matter. But they're all canceled out because all those hydrogens point off in all directions. Whether it's a chain, whether it's got a double bond or a triple bond, or whether it's the benzene ring, everything's pointing off in opposite directions, and all of those dipoles cancel out. So hydrocarbons are non-polar. They are the types of molecules that you would encounter in gasoline and propane and grease and plastics. Yeah, all those types of things. So what are the intermolecular forces that govern them? Well, London forces. That's what takes place if we have non-polar molecules. The bigger the molecules, the more electrons they have, the stronger the London forces. All right? Propane is a gas, right? But as you add more and get to octane, which is in gasoline, it's a liquid. All right? So as you have more and more carbons, the stronger the London forces, the higher the melting point and boiling point. Paraffin wax is an example of a solid hydrocarbon, and paraffin wax typically has around 30 carbons in each of the molecules, and there's so many carbons, the London forces are great enough that it results in the wax being solid. Branches reduce the strength of the London forces since the chains can't get as close together. With all those branches hanging off of it, they can't kind of get really close so that they can feel those London forces, because they've got to get close enough so they can feel the nuclei of the other molecules. Hydrocarbons have low melting points and boiling points. Okay, next. Let's get rid of this guy here. Next. Reactions of hydrocarbons. Well, as we've seen in the past, yes, we are fully aware that hydrocarbons can burn. We can burn them. I've burnt many hydrocarbons for you over the years. No, I'm not going to shoot a rocket car or explode propane bubbles. We'll just have to think back to those good times, grade 11. Good times. Here I've got some various hydrocarbons, all right, that I'm going to ask you to complete and balance the chemical equation. So let's balance these up. The reason I want to do this, and I'll explain it to you in a minute once we get it all balanced. If I give you a chemical reaction to do on a test, and I have some kind of hydrocarbon plus O2, I need you to know that it's going to be a combustion reaction. And if it's a hydrocarbon, what are my products of the combustion reaction? Carbon dioxide and water. Excellent. That's one of those that I've been trying to convince you for a long time. When balancing something like this, squeeze everything together. C2H6. All right? Makes it easier. Balance up the carbons. 2 carbons, 2 carbon dioxides. Always. The number of carbons is equal to the number of carbon dioxides. Hydrogens. 6 hydrogens. Divide by 2. 3 waters. Don't worry about the 0.5s. Leave the 0.5s in. I always think of oxygen in terms of the 0.5s. So when I'm calculating oxygens, I'm thinking about O2s. How many O2s can I make? Here, always same number of O2s. I got 2 O2s in that carbon dioxide. Here, there's single O's. So how many O2s can I make out of 3 single O's? 1.5. 1.5 plus 2 is 3.5 O2s needed for that. Okay? Let's do the same thing here. C2H4, CO2, H2O, 2, 2. In this case, I only need 2 waters. So how many oxygen? 3. Notice, I get rid of 2 H's by turning the alkane into the alkene, and it means I'm producing 1 less water, okay? Which means I need half an O less, because every water supplies me with half an O2. So I need half an O2 less. And as I move on to this one, C2H2, again, CO2, 2H2O. Sorry, not 2 necessarily. I'm looking ahead at the top. Actually, it won't be 2. And what have I got? 2 CO2s again, because I got the same number. And now I only need 1 of these guys. And again, now I need 2 and a half. 2.5. Okay? So hopefully this isn't too earth-shattering when we look at it. Every time I have another degree of unsaturation, I need 1 less O because of the waters, 1 less water, and I only need half less of the O2, all right? Now, if we did the calculation of delta H's, if you look back at those delta H of formations, carbon dioxide and water, when they are formed, give off large amounts of energy. The energy we get from combustion reactions come primarily from the number of carbon dioxides that are formed and the number of waters that are formed. And the more carbon dioxides and more waters that you can form, the more energy you get from the chemical reaction. And so if I look at this reaction, I'm actually going to get the most energy out of burning the alkane, because I'm going to get more water formed, and for each water that is formed, energy is given off. Another way of looking at the energy releasing ability of a hydrocarbon is looking at the amount of oxygen that is required to burn it. The more oxygen that's required to burn it is also related to the amount of carbon dioxide that is formed and the amount of water that's formed, because each one of these has O's in it, right? So if you need more oxygen to burn it, you're going to get more energy out, okay? And like I've said in the past, all of these have to be in the gaseous state. And I don't know if you recall, but gas molecules behave the same whether they're small or whether they're big. So if you take something like octane, which has 8 carbons and 8 times 2 plus 2, right? So what's that, 16, 18? 18 hydrogens. You're going to get a lot of carbon dioxide and water, and you're going to get a lot of energy out. All right? So when you have something like propane burning in your vehicle, because you can get a propane-powered vehicle, per molecule, you're getting less energy. You're not going as far per molecule than you are with an octane, because it's loaded with potential energy in there to produce lots of water and carbon dioxide. You have something like a diesel engine that has like 12 carbons in them. Diesel fuel has 12 carbons in them. You actually get more energy per molecule out. Okay, so they all burn. Neat little bit of information to keep in your mind. The more oxygen you need to burn the molecule, the more energy you're going to get out. The more energy dense it is. Okay, now let's talk about some, you can put in the title, reactions of alkanes. Now that last one was just a general reaction of hydrocarbons. All hydrocarbons will burn. Now let's talk specifically about alkanes. All single bonds. Okay? Obviously they can burn. And yes, it's fun when we burn stuff. But we want to now talk about other reactions they can undergo. So the first reaction I want to introduce you to is something called a substitution reaction. In a substitution reaction, it is exactly what it is. We take one of the H's off and we put something else in its place. Typically what we put in its place, halogens. And then if we want to get more creative and put other things in its place, we tend to then remove the halogen and put something else in its place. I'm sorry, but I've got to bring a hockey analogy onto this, or you could use any sport if you'd like, but I play hockey. And, you know, if you want to, if you've got your full number of players on the surface, we'll keep it hockey neutral, full number of players on whatever playing surface it is, if you want to put another person on, you've got to take someone off, so you've got to take someone off before you can put them on, and it's called a substitution, right? Substitution ref in hockey or in soccer, you ask for a sub, right? In hockey, you don't actually have to ask, but you've got to make sure you get them off before you put them on, right? And so it's called a substitution. And it's the same thing here. It's a substitution reaction. We have to remove one of the H's. Why? Because we're dealing with a saturated hydrocarbon. It's right full of H's. They're all single bonds. And so if you want to put someone on, you've got to take someone off. And that's what a substitution reaction is. So it's fairly slow because you actually have to pluck one of those hydrogens off. And because all of the hydrogens are identical, you really don't know which hydrogen is going to come off. And it can be done. It's slow, but you need some ultraviolet light. That tends to make the bonds weak. So if you hammer one of the bonds with an ultraviolet piece of light, we call it a photon, it makes it weak, and that can cause that H to fall off, and then you can have another one come in its place. All right? So let's do some examples of this. So I'm going to just draw out a little structure for CH4. CH, H, H, H. And in this case, the structure of bromine is not important. So I'm just going to write Br2. And in the end, you're going to get C, and one of them is going to be a Br. H, H, H. And it tends to need UV light, so we'll write that over top of the arrow. That represents the fact that we need UV light. And then when you're done, you end up with the H bumping into the Br and creating an HBr. Okay? And now we've got a new type of chemical that we can name. In other words, we've got a new branch. And we can give that branch a name, just like we gave the phenyl, right, for the benzene. So this is actually called bromomethane. So bromo is the name for a bromine branch. Even though it's not really a branch, it's just an atom, we call it bromo. If it was a chlorine, we'd call it chloro. And if it was an iodine, we'd call it iodo. And if it's a fluorine, we call it fluoro. Yeah, the periodic acid, that's always fun too, yes. So the thing is though, this doesn't stop. It continues on. So now we've got a Br, an H, an H, an H, and again, it continues to react in the presence of that UV light. So in this case, now I'm going to have a Br, and I'm going to have a second Br, and an H, and an H, and it's going to produce another HBr. And what do you think this one's going to be called? Yeah, dibromomethane. Dibromomethane. If there was a chain and I had different spots, I'd give them numbers. I'd still call it di. I would treat it just like any other branch. So this is dibromomethane. And I'm going to just put here, down here, et cetera, because it is going to keep going. I'm going to put 3 dots here, and I'm going to just put the last one that you'd end up with, Br, 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 Br. In other words, it would become fully substituted, we would say, fully substituted. And what would this one be called? What's the prefix for 4 when we're talking about branches? Yeah, tetrabromoethane. Okay? So that's a substitution reaction. Let me show you one more example of this. And I'm going to just show you with propane, just to tell you how to draw it or name it if it's a little different. So I'm not going to write this out here. C3H8, we'll draw this out in a moment, plus. And this time I'm going to add, and I'm going to add just, let's add 3 of them, 3I2, okay? In other words, it's done 3 steps. It would go all the way to the end. It would add all 8 of them if you kept giving it ultraviolet light and you gave it some, and you need UV light. Again, I want to stress this is a slow reaction because we're going to do a little experiment with propane, and we're going to see if we can see this reaction because iodine is a purple color, and when it is substituted, the purple disappears. And this is phenomenally slow. This is what we want to test. Yep. We know that if the right color of light strikes an atom, we can get the electrons to jump to a higher orbit. It's also true for our bonds. Remember, our bonds now are made up of overlapping orbitals, and those are now called molecular orbitals. They're an orbital shared by a molecule. If you strike those electrons with the right color light, you can get those electrons to jump to a higher orbit. When a bond's electrons jump further away from the nuclei, the bond becomes weaker because now they're not sitting in between anymore. They're further away because they've been excited to a higher state, just like in an atom. So bonds electrons. So the electrons in one of these H bonds, let me just put an H here just for the sake of it. So if I have a sigma bond here, and that gets struck with UV light, the electrons get excited, it makes the bond weaker. It can be excited so much that it makes it so weak that the H just goes away with its electron. It just makes it fall off. You break the bond essentially by making the electron jump so high. And it turns out that ultraviolet light is the right color of light to make that happen for a carbon-hydrogen bond. And that's why it happens. Okay? So the UV light hits it, and let's put an I over here. Let's put just an I on this one. And because we're doing with 3, I'll put a second I on this same one here for no reason, because there's no way to predict which one is going to fall off. If I asked you to do this, you could put 3 I's wherever you wanted. And I'll put another I on this one here on the outside one, again for no reason. Again, we've got H, 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 and H. And the key is that one of the I's ends up on the C, and the other I ends up on the H that has come off. They form a bond. And the only reason I wanted to kind of illustrate this was to say 2 things. 1, there's no way to predict where the H is ending up. And 2, just so that we can name this guy. So, main chain on this guy here. It's a propane chain, right? Propane. I've got 3 branches. 1, 2, 3. They're all iodine, so they're iodos. And there's 3 of them. So it's triiodo. It's kind of fun. And each one needs a number. Which of these carbons is going to get number 1? This guy here. Because I've got 1, 1 then if I do it that way. If I do it this way, I'm going to have 1 and then 2 3s. And I've got to have the smallest number possible. So this is 1, 1, 3. From the other end, it would have been 1, 3, 3. And that's bigger than 1, 1, 3. 1, 1, 3, tri, iodo, and no space propane. Okay? That's a substitution reaction. And there is a little list of the different branches. If you might get that already, you might not even need to write that down. If you need to write that down, you can. F branch is fluoro, Cl branch is chloro, Br branch is bromo, and we just encountered the iodine branch as being iodo.